So, good morning. I'm Krishna Kumar from Krishna's classroom. So, last time we discussed the outline for the proof of the cyclic decomposition. Now, let us take up the details of the proof. And this is the second part of the discussion on the proof. It is since it's a lengthy proof, I think we will discuss it rather slowly and systematically, so that try to make it as transparent as possible. So we start with the proof of the step one. Step one consists of the proving the existence of certain set of vectors u1, u2, etc. and ur, from which the vectors v1, v2, vr that are mentioned in the statement of the theorem will be manufactured inside. So that we will come to in the third part. But before that, we get this how we arrive at a set of vectors u1, u2, etc. ur. Okay. So let us start. Now, as I said in the beginning, that there is no harm in assuming W not equal to 0, but however that does not really simplify the proof in any way. Therefore, we shall assume that W naught is proper like this. So in step one, what one does is the following. I mean, there will be a lot of repetitions, which I think you will probably may dislike, but certainly it is worthwhile to recall some of the facts over and over again for the clarity, for the sake of clarity. Now, in step one, we identify vectors ur belonging to V such that A U1 P. So that is that's the first thing. The second property that is desirable is this following. One R and WK is defined as P then the conductor the conductor dk is defined as the one that carries UK into W K minus is the one has maximum V among all P conductors into the subspace K minus. So what we do is the following. We define PKV E to W K minus 1. Now this is a T conductor of V E to W K minus 1. I will explain. And what we want is to choose a U. So U is chosen such that Pk, degree of Pk, which is equal to maximum of V belonging to V of S minus 1. I think for clarity I can write here. Okay. So you see that how do we actually zero in on the vector V? In fact, there are several choices of such U's available from among one of the mutuals. So it's easy to show the existence of such U. Okay. Now we will make some remarks on this. How UIs are. See, what you are doing is the following. Suppose W is a T invariant subspace. Now what you do is you start with any V or any V, and you see that there is a PK which carries it to that belongs to this space, and PK is what we call S. PKV is S V W K minus. Now for each V there is such a PKV. Now we choose V such that the degree of PKV is maximum. Okay. So we choose U such that degree of this is how we make the choice of. Okay. So how do we get this U1, U2, etc. UR? We do it recursively. Okay. So we start with the W0, then choose U1 using this idea. Then what you do? The next step, you look at W1, which is equal to W0 plus Z U1T, and then choose U2 using the same idea with the W0 replaced by W1, and so on. And this process has to end in a finite number of steps, because every Z UR UIT that you make has dimension greater than or equal to. Therefore, since V has finite dimension, it will get exhausted in a finite number of steps. And say we designate this number of steps by R. Okay. At the end of the proof of this theorem, we will prove that the choice of this R is unique. So let us just describe this probabilities. So this is how we choose the UIs. So let us do that. So we have W0 is now we use this idea. Okay. So we have, if W is invariant under T, this is what. So in the figure, choose a V such that degree of contains an answer. All this vector and the choice of U is not unique. There may be several such choice, as we have seen in the example that we have already. Now what happens is, you have a certain U here which is mapped to into W, and degree of PK V or PKU the degree of pKu is the maximum that is possible among all the choice of u that we can do. That's how we choose. Now what we have is, you see that upon what we have is 0 less than or equal to 0 less than degree of yes. Now you look at the subspace. Cyclic space generated by then this is also all these computer. Then this is also and dimension of is strictly greater than this facts we observe. Now what we do next is we continue this process or apply this process with starting with the choice of W as W. So starting with we identify that's not the choice. Now define W1 to be W plus W0 plus then W1 is invariant under P. What we have is that W1 is invariant under P. Apply the same process. If you apply the same process, you will identify a U2. If W1 is already not equal to V, then you can find a U2. And such that W1 is properly contained in W1 plus Z U2. And this inequality holds for W replaced by W1 and U replaced by U2. You go to construct, you get W2. Okay, right? Then construct Then apply the same technique. Process to identify U2 so that and if W2 is still not equal to V, we continue the process. Okay. Continue this process. To now this process has only finitely many steps. Since dimension of strictly less than and B has this matrix. So at most you may have to work through a finite number of steps which is less than the dimension of B. Or maybe if you go through one step or one dimension at each step, then you are going to end with n. If the starting point we have W0 as dimension 0. Okay. So let us. So we have found a way of obtaining the U1, U2, U3, etc. So the scenario is this: you have V. You start with W0. You have then you have some U2. This goes into so this is the sort of diagram that I want us out of this. So you have got with U0 you have U1, with the Wk minus 1 you have Uk, and so on. In retrospectively we get this U1, U2, etc. Now you immediately observe that these vectors are immediately because you see that k minus 1 is certainly inside Wk dimension, but Uk is outside that. The observation. So the second step, in fact, goes further to prove that these W Ks that we obtain are all P admissible. Okay, so that's the next step. Then only you can run the scheme, because W naught is P admissible we are assuming, and we are constructing recursively W1, W2, etc. W up to WR. Now we want to, for the later purpose of constructing our V1, V2, etc., VR, we need the P admissibility property of W1s. Okay, so that's the reason why we want to prove that. So in step 2, we in fact prove that all these WKs are limits. Okay. So step 2, just get that. So now we can pass on to the next step. So we have now a method of identifying this U1, U2, etc. So in step 2, we prove that each of these Wi's are P admissible, so that we can construct our Vi's, because so far we have only got some Ui's. Now from Ui's we have to pass on to construct Vi's to get the statement of the theorem true, namely that V can be written as W0 direct sum ZB1 B direct sum ZB2 B, etc. direct sum ZBR. So to obtain that statement, we have to get hold of this V1, V2, etc. So step 2 is here we each Wi is this is essential to construct to obtain VR from the vectors as we shall see in part 3. This until that you will. But our limited objective is now to show that this is here this. Let us see how this works. Okay. So we have identified U1, U2, UR, which are non-zero. Such that A and B, A is such that for one WK equal to W naught plus UKT, then the T conductor PK defined by S as maximum degree among all T conductors. Into the subspace that is for every Q. Degree of maximum among B belonging to B so what I want to just repeat this, you choose the U such that the maximum is from among all the V's you obtain U which has this degree of the T conductor. So that's maybe repeating it over and over again, but still, maybe for clarity. Okay, let's look at that. So that is K V G. So choose B. For which degree of pKb which is equal to degree of maximum, and such a U, such a V that's how we have made the choice. Now what we can say is the following. So what is happening here? Suppose we have done it up to a certain K. Then you want to do it, go to the next step. Or we have done it up to Wk minus 1. That means you have identified Wk, and then you can go ahead to the next step. Okay, so let us see this. So let define by F yes, it's good. Now, if we prove the following, this is the major thing that we do is show that if FTU equal to U naught plus sigma 1 less than or equal to I less than GIT UI where UI the left device GI for everything. This is the statement. And also U naught is equal to for some U naught belonging to W. Okay, so what do we prove here? Look at this expression that is written here. Okay, you know that the U naught is an element of W. Okay, because we are writing Wk equal to W naught plus ZUKT. This is what you have. Therefore, look at this vector. Where does this belong to? U0 is in W0 and G1T U1 is in ZU1. Okay, and so on. Because what you see that what are the vectors in ZUT? See, in ZUT you see that the vectors belonging to ZUT are polynomial operators acting over U. So that is the important point. So what exactly is the vector that we have written here? See, you have U here. U has been mapped by Ft into Wk minus 1. And Wk minus 1 is essentially a sum of a vector in W0, a vector in ZU1T, etc., a vector in ZUK minus 1T. What are the vectors in ZUIT? See, ZUIT consists of all these vectors GT UI, where G is a polynomial over F. Consists of all these things. Therefore, you see that FTU being in WK minus 1 is a sum of a vector in U0 plus a vector in Z U1 T, etc., a vector in Z UK minus 1 T. Okay, so you see that if you look at this one, see GIT UI belongs to where Z UI okay, this is true for each I. So therefore, you see that it's a vector in W0, it's a vector in W1, and so on. So it's something like this. You have got V, you have W0, you have W1, etc. You have A minus 1. So you have a vector U0 here, a vector in W1 here, etc. W, a vector in WK minus 1. They are all polynomial operators mapping the corresponding UIs. Okay. Therefore, this particular vector that you have obtained here belongs to, therefore, FTU W. Wk minus 1 is successively built from W, starting from W. So this is a Wk minus 1. And of course, now we start working on this. So what we assert here is that all the GIs are divisible by F. Okay? So the claim is that in other words, you have GI equal to H for some the X is polynomial X, right? Such that this is. So we have to prove this. How do we prove this? We do not know. We want to prove this first. So when you want to prove this, what you observe is that anyway, GIs, when you divide or use the division algorithm with F, what you get? So we have the following. That is, what you have is the following. When the GI Fxi plus R. This is the remainder. And what you have is this either Ri equal to 0 or degree of Ri is less than degree of. This is the division algorithm applied to this. Therefore, let us know how to do this. So what we want to prove is that so we do a recursive argument. Now observe that for k equal to 1, this statement is what happens for k equal to 1? It simply says Ft equal to the corresponding Ft U0. And U0 is in. So you have got the U getting mapped into W0. F is of course generic here. It is a corresponding what is called P conductor or associated with UN. So this is trivially true. And T being, so what we have is that since W0 is P admissible, there exists this is some V belonging to some V belonging to some W belonging to W naught such that W equal to that's a statement that here. Okay. Now we want to prove this for every Wi. If you want to prove that, you will have to first prove every Gi is divisible by 10. That's simple. Now we establish yes or no. K greater than 1. That is what we want to do is we have Gi equal to F Hi plus Ri. What we see here? Then Ri equal to 0 or degree of so this is in general, and we want to be sure that R is equal to 0 for each time. So that what you have is that each Gi is Hi for some Hi. That's our next task. Okay, let us do this. Before that, we do some working backwards. Working backwards, tell you the following. See, we have the statement that FTU equal to okay. So what we have is this. We do a little bit of working backwards. So what do you have? We have the following statement. FTU equal to U naught plus sigma 1 to k minus 1. Gi I rewrite as in this one. Therefore, what I get is Ft HIT UI plus this is just writing out. You see that this is essentially Fi F HI plus RI is equal to GI. Okay, this is from it's a restatement of the whole thing. Now what one does is the following. So you have FT 1 to k minus 1. FT I will take up. I bring this here, this particular term here. Write this as right? Equal to mu naught plus Qi. Just the restatement. Now what I do is I define this as what I have is with that definition you get FTB equal to this is the relation that we get. Now if you prove that Ri is equal to 0, then you are getting FTV equal to mu naught. What does it mean? It means there exists a V such that FTV equal to. Okay, so mu naught is a multiple of or a is Ft times some vector. So the existence of such a vector is. So our objective is to prove. So V which implies so this is what we want to so let us now formally do the whole job. So define V equal to U minus summation 1 to k minus 1 HIT. This is the definition. Look at the status of this suit. Okay. Now one thing that you observe is this, if that is so, then U minus V belongs to, this is W I minus or W K minus. And this implies the following: S of k minus 1 which is 0. Okay, what is that you have to prove to get this statement through? So I give the proof like this. Suppose see, this is the reverse version of the C. Okay. Now, suppose you have U and V are two elements. Two elements. With the property that W is equal to U minus V. So, suppose U and U minus V. If U minus V belong to W, then what you can prove is the following. S of not the polynomial but the class of one polynomial of kind of this that you have. This is equal to the set of all gt belonging to G belonging to X such that gt of B belongs to. Now you can show that GTV implies GT U belongs to Y. Why is it so? Because W is equal to belonging to W. That is the reason. That is the reason. Which implies yes. Now reversing the role of we have S or S which implies you call this. So this is the result that we got. This is the inference that we generally we apply this, therefore we get a corresponding expression. Therefore you get you write using this you get yes. That's the result. Now we want to prove, come back to the original. problem. We wish to prove that Ri equal to 0, and if Ri equal to 0, then this is the consequence. We will come to the consequence later, but before that, we first try to prove this. How do you prove that? So you prove this. Okay, so let us prove this. So we want to prove that you know that the degree of Ri is less than the degree of F. That's how the remainder comes. So if we are able to prove that degree of Ri is greater than or equal to degree of F, then we are done. Okay. So we first prove that there is that we take on if Ri is not equal to 0 for certain I, then we prove that this is degree of F. Okay. So that's the step. Suppose suppose J is the largest index I for which Ri is not equal to 0. But we are going to prove is that every Ri is equal to 0. Then what we show is that what we have is this F3 of P equal to U naught plus sigma 1 to j Rj Ri and degree of Rj so let P be S V now Wj minus 1 is contained in Wk minus 2. That is clear from the way in which we have the inequality, the corresponding inequality actually tells us that this is. Therefore, so the T conductor F, which is equal to K minus 1 divides that is E equal to F. How does this come? See, this comes like this. You have got you have a Wj minus 1. This is the now F going to see you are taking the what's called T conductor of Vb to Wk minus 1 and Wj minus 1. Okay. So the T conductor of V to W, because of Wj minus 1 is contained in Wk minus 1. So once it goes here, it means it goes inside Wk minus 1. Therefore, what happens? You know that the minimal polynomial associated is called the T conductor. The T conductor of F, the relation between F and P should be such that P is equal to F. Okay. That means what you can say is that F divides now we take up our old relation. What is the relation that we have? FTB equal to this is the relation. Now we apply GT to both sides. So what do you get? So GT of FT of this is equal to, this is in fact equal to PT of P. Okay. But this one, this is now equal to GT of therefore, let me write, I can write this is equal to, I'll split up certain terms from here. So I get GT RJT UJ. So let me write that. UJ plus GT U naught plus sigma 1 to J minus 1 GT R I T. This is the term. I have just taken out one term from here and from here. That's all. That's the only difference. So what is the consequence of this? Now let us work on that. Out of which you see that these two terms are in Wj minus 1. Okay. So these two are in Wj minus 1. And what about this? This is also in W. Okay. This is in Wj minus 1. Therefore, the consequence is that, see, we have PPE and W naught, what is that? Sigma J minus 1 GT U1. They belong to which in turn implies so this term, this is in Wj minus 1, this is also in Wj minus 1, this is also in Wj minus 1, which in turn implies that this is in Wj minus 1. So this means Gt Rjt Now we make use of this relation. Okay. So what we can say is this is important. So degree of GRJ is therefore greater than or equal to degree of S Pj minus 1. That's an immediate consequence of this. Okay? And that's equal to degree of Pg. And this will go by Pg. And this is greater than or equal to degree of S which is equal to degree of P, which is equal to degree of G. So what you get is degree of GRJ is greater than or equal to, which in turn implies degree of so this is what we want. But we know that degree of R is less than, so that's it. Okay. Therefore, you see that the choice of J that we have made is not possible, which in turn implies Rj, Ri, So what is the consequence of this? Suppose Ri equal to 0 for every I, then this is what you have. This implies Ft okay. Now since here principle, we have u naught is equal to for some u naught so that completes the proof of the theorem. Okay. So as I said before, that we have the from what we have started with, we have FTV equal to, so you get FTV equal right? So that can be simple. Where V is of course V belongs to so this is the proof of the second part. So this in turn tells you the following. See, this is we have worked on a particular K. Now we can recursively work on this. Namely, we start with the W0, then on W1, on W1 we prove it, and then we go to W2, and so on. We can prove for all Ws. Therefore, what we have proved is that each one of these Wj's are, hence we have proved that we have proved that everyone we have this result not now that allows us to use this particular property for any W, and that completes the proof of part 2. Now let me say what we propose to do for part 2. That means step 3 and then the statements about and the statements about and in step 4 is the boundary. So the existence proof has been partly done, not completely. Only after we establish that the existence of V1, V2, etc. VR, the proof will be complete. So we have now arrived at V1, V2, etc. From where we go to expect this V1, V2, etc. So thank you very much.